Okay. So, for the Gaussian random variable, we have already started discussing about mean, variance, standard deviation. So, let us try to characterize those things now. Okay. What do we mean for a and how they are related to a corresponding PDF or CDF. So, that is something which we will target in this class. So, let us first try to see the basic or classic definition of mean, which is just the average. How do you do averaging? You actually, suppose I go to a class and I say, okay, I want to get the average height of all the students. So, what do? You actually ask every student their height, you note them down, you add them together and then divide it by the number of students, right. That is how we calculate average. So, this is a well known thing. Okay. Now, suppose we want to do this in a little different way. We say we want average height, but we want to just do this with an integer number. Okay. So, it is 5 feet, 6 feet, 7 feet or 4 feet, something like that. Okay. We will have no other things. So, basically what we will say that if somebody is having height from 4 to 5, we will report that as 4. Okay. If somebody whoever are falling from 5 to 6, we will report that as 5 and so on. Okay. If I just do that, then it will not be single observation for each one of them. Okay. So, we will have to then see how many of them are falling under that category and then accordingly we have to take. Okay. So, what will happen? It is like this, we will probably means after doing that we wish to calculate the average. So, then we are saying, okay, how many of you are between 4 and 5? We will take that number, let us say that number is N1. Okay. So, and for each of them how much I will be evaluating, that is to me it is 4, or I can take that as 4.5 also. Okay. Whichever I take, that N1 into whatever that value. Okay. So, let us say that is x1, I will do that, and then I will also calculate how many are of 5 to 6. So, I will take the number, I will multiply by the number that it represents. Okay. X2, it might be 5.5, okay, something like this, and I will do for n number of such things. So, let us say n number, last one I get xn, and then I will divide the whole thing by the overall number of students. So, which is nothing but sum of this ni. Okay, in each category there were n1, n2 or n3, ni number. So, I will divide by this. So, that gives me a sense of average if I do it this way. Okay. Otherwise also it is true, means this was a specially created experimentation, but if I wish to calculate, suppose I take a coin and I say if it is head then it should be +1, or if it is yes, if it is head it is +1, and if it is tail it is -1. We have already told random variables means it has to be mapped, whatever events are there that has to be mapped to a real axis. So, we have mapped it -1 and +1, and now I do this experiment for let us say 5 lakhs time, okay, and then I count how many heads have occurred. I multiply all of them with +1, and how many tail has occurred, I multiply all of them with -1. Okay. So, that as many numbers into +1, as many numbers into -1 and divide by the total number, that is how we evaluate things. So, it is always true. For a die also it will be similar thing, there will be 6 such part, right. Now, let us try to see little bit more carefully. So, this n1 divided by summation ni, that is a factor which is coming into x1, right. We will be always getting this kind of factor, n2 divided by summation of ni. Okay. This summation of ni is actually the amount of time I have done that experiment, repeated that experiment. So, that is n. My frequency definition or probability was that n I go take it towards infinity. So, once this is going towards infinity, what happens to this? this actually tells the probability that this x1 will be happening. That is what we have defined, that is how we have defined it. Okay. So, for head and tail, if we just take that from 5 lakhs to maybe 5 crores or even more, then almost half the time it will be head and almost half the time it will be tail. So, how many times it has occurred, that favorable things has occurred, divided by as many times the experiment has been run. So, this ratio is always in frequency term gives me the probability. So, this must be, as summation ni tends towards infinity, this must be the probability of associated random value x1. So, I can write this as p x of x1, okay, that x1 will be happening into x1, plus this I can write as p x of x2 into x2. Similarly, it goes on. Okay. So, immediately I can see the x bar is nothing but, in a discrete case, as many times I will be doing this experiment, right. So, that is the famous definition of mean. So, mean is nothing but your random variables are there, all possible things you take and you multiply with associated probability and you add it up for all the possible outcomes, whatever you get, that is the mean. Okay. So, from the classic definition of mean, we could see that this is the definition of mean with respect to its associated probability. Okay. If we just extend it from summation to integration, that is how we go to a continuous one. So, immediately that summation will become the integration and inside it will be associated PDF. So, I can write x bar if it is a now continuous variable. So, that should be, now the summation will become integration from minus infinity plus infinity in the entire real axis where this can happen, x into pxx dx, right. So, that is for the continuous variable, right. So, we get a associated mean. So, this is how mean being calculated, and that is why probably that PDF is so important, because mean is something which is called the average. So, whenever there is a randomness happening, you tend to get the average, try to guess the average, what is the average of it. So, on an average what should I expect from this random experimentation. So, whenever you try to guess that average, you need to have this PDF, associated probability density function of that particular thing, or for the case of discrete variable, you need to have that PMF. So, either PDF or PMF you will be searching, because you know that through which you will be able to calculate the associated mean, one of the measurable parameter. Okay. Now, let us say if I have a function of a random variable. Okay. So, what do I mean by that? Suppose this x is a random variable and what I get is, there is a function which maps that random variable to some other real axis. So, it is just a functional mapping, whichever way you wish to do that. Okay. So, suppose there is something called temperature variation. Okay. So, something varies with the temperature square. Okay. Now, temperature in a day is a random variable. You take that and that targeted variable is varying with temperature square. So, it is mapping that random variable to that particular temperature square variable what you have defined. Okay. So, that kind of thing. So, that will be a definitely another random variable which completely depends on your input random variable. Okay. So, that if I just say as y, now I might have to finally, I might not observe the temperature, but I might observe that outcome, which is the temperature square probably. Okay. So, that is how I can measure things. So, I might have to get my y bar, okay, whatever I am getting that random variable. So, I might, this y is also a random variable which is just eventually a function of another random variable. So, I need to evaluate the mean of that. So, what happens if I wish to calculate y bar, that should be just this g x bar. Okay. So, whenever there is a x happening, right, I means to calculate the average, I was multiplying x with its associated probability. Now this x will change to gx, right. The associated PDF is still on x. So for each value of x, that is the if I just correlate this probability to frequency term, that should be the case. So I can always write this as summation if it goes up to n. So gxi into its associated probability, right. So this is something I can always write, or in a continuous one it will be just integration. So gx bar must be minus infinity plus infinity gx, right. So similar definition, it is just instead of x it has become gx. So this is more generic. If gx equal to x, then I get the earlier definition, that is the, because it is a one to means direct mapping, it maps to itself, right, one to one mapping and maps to itself only if gx equal to x. If any other thing, it will still have some kind of mapping, and I will take that associated probability and I will still get the average of that. Okay. So this is the functional average we talk about. Now let us say, suppose I have a joint thing, okay, where there are two random variable x and y, and they have a joint PDF which is defined as pxy xy, and I also have a joint function. I want to evaluate the associated mean. Okay. So that will nothing but the same thing. I will have to multiply for each xy with its associated PDF and then integrate over the entire means domain of x and y. So if I wish to calculate gxy bar, that must be minus infinity plus infinity minus infinity plus infinity, this pxy, and this should be multiplied with gxy, right. So that is the average of gxy that we will be able to calculate if I do it that way. Okay. So if this is the case, I can also now start writing, if I have a g1 xy, that is one mapping, and another g2 xy, another mapping, random variable remains the same, I wish to evaluate the average of this one. So this is very clearly, it can be seen that this g1 xy, g2 xy will be separated out, then 2 integration will be separated out, and I can immediately tell this should be nothing but g1 xy bar plus g2 xy bar, right. So this is very true, because once you replace this whole thing over here, then 2 integration will be separated out and I will get this same result. So any functional mapping, if to addition of functional mapping, if I wish to get the mean of that, I will be getting, means I can separate them out as if I calculate the functional mean of the first function and functional mean of the second function and I add them. Okay. So this is always true, that is pretty obvious from the integration definition of, or through PDF, the way we define mean, right. So now I can just say that this g1 xy is nothing but x and this g2 xy is nothing by y. I can have this functional mapping, right, that is always possible, that it is a function of x and y, but probably the y coefficient is 0 always, and this is also a function of x and y, but the x coefficient is 0. So this can happen, this is a valid function. If I just put it over there, so what will happen, my x plus y bar is always x bar plus y bar. So this is always true. For this to happen, you do not need anything, remember, no independence among x, y and all other things are required. Mean is always additive. If you take two random variable, whether they are independent, correlated, whatever it is, you do not care, the mean you can separately calculate the mean and you can always add that. So this is telling you that. Okay. This is something which is very important, you should always remember that for mean you do not have to think whether those two random variables are at all dependent or independent or any other relationship they bear. You do not have to care about that. You can always say, okay, if I can individually get the mean of these two, I can always add them up, that should be the overall mean. This is always true. Okay. Now, let us see if this g x y is nothing but a product of two functions, where they are separately just function of x or y. Okay. If this is the functional mapping and this is the nature of these two functions, then how do we evaluate the overall mean value? So, let us say I want to still get g x y for this particular function, the mean of that, right. So, I can again write minus infinity plus infinity minus infinity plus infinity. So, this is g x y p x y x comma y dx dy, right. Now, I know that this can be separated, right. Now, the question is if this can be separated, what is the condition where we will be able to separate these two? If x and y are independent, then immediately I have already proven that this can be written as p x x and p y y. Now, the integration can be separated out. So, I can write this as g x into p x x dx and integration minus infinity plus infinity g y into p y y dy. So, this is nothing but g x and g y is right. So, this will always happen. Remember, not necessarily this joint function has to be same mapping g. This can be g1, g2, whatever it is. Okay, that might be different also. So, in that case, it will be just g1, g2, whatever it is. So, this will be g1, g2. So, this will be g1 and g2. So, the mapping can be different. The one we have taken, probably that's a specific function. We all know that for Gaussian that is what happens, but you do not have to really have that similar kind of mapping. Anyway, whatever that mapping is, you need to be it should be possible that you separate them out. Okay. So, and you can put them as multiplication, where one part is just a function of one of the variable, other part is just a function of other variable. As long as this is possible, and if the random variable, that is x and y, those are independent, then you know that the overall this functional mean is just the multiplication of their mean. Okay. So, if now that function I take as x and y, x multiplication y, that is separable exactly, because you have just this multiplication this is just a function of x, this is just a function of y. So, that has happened. So, my g x y is nothing but x y, and g x, this is also a typical example where both are remaining as same function. So, this is x, g y is just y. Okay. So, as long as this is happening, I can write this when if x y are independent. So, this is a strong condition. If two of the random variable are independent, then their mean means mean of multiplication is nothing but the multiplication of mean. So, this is a very strong condition for x y this always happens. So, x y bar is equal to x bar into y bar. Okay. Now, let us talk about some of the higher moments. Okay. So, mean is, we call that means most of you will be knowing already, that is the first moment actually. The higher moments are defined as this is by definition. So, x n bar, that is defined as this. Okay. So, just higher moment, why mean is called the first moment, it is just because n equal to, if you just put 1, you get the equation of mean, right. So, that is why mean or average value is the first moment, and then if you just put it as 2, that has a specific name. Okay. So, that is the second moment, and then from second moment you can actually get variance or standard deviation, that we will talk about now. Okay. So, when we talk about variance, we are actually mean by this. This has a big significance in any statistical process. What it is saying, it is actually whenever we write this, that means we are taking an average. Okay. So, that bar means average. This x is a random variable, right. We are picking different values. What we do, we first calculate the mean, and here what we are trying to do, for every value of x, we are actually taking how far it is from the mean, okay, and squaring that, because if they are on both sides of mean, then they will cancel each other if I just add them together. Okay. So, we square and add them, add all of them, divide by as many random samples are there, divide by that n, I get this average value. So, this is actually saying, means it has a physical significance, it is saying how far it is deviating from its mean value. Okay. It is the square of that deviation. So, basically you are taking all these samples, if this value is very low, that means immediately you can say most of the values are lying very close to the mean value. If this is very high, that means it is flatter. We are talking about that Gaussian with sigma square, low or high, that is the case. If it is having a higher value, that means most of the values are actually lying away from mean. So, overall mean can be seen, I might suppose the height of a particular class or section. If that is reported from, it is all over the place, suppose let us say from almost 4 feet to 7 feet, everything you observe. Okay. So, then you can say that maybe the mean value is still 5.5 or 5.6, something like that. Okay. But there is a huge deviation, this might happen, whereas if I just do it for the age in a particular class, what will happen? They will be all running very close to the average age, because generally in a class we just give admission if their ages are almost similar, right. So, if you do that, so for age what will happen, you will immediately see that their ages are not deviating too much from the mean value, whereas height or any other weight, if you start observing that, you will see a lot of deviation. It might vary quite randomly, and there will be a huge deviation. So, in that case, see, just mean does not characterize anything for a particular random experiment. So, if the mean, suppose for 2 random experimentation, the mean might still remain same, but it might deviate quite small from the mean value, or it might deviate heavily from the mean value. So, these 2 samples are quite different. If you just observe those 2 samples or those 2 random outcomes, you will see they have a huge difference, whereas probably mean will be still the same. Okay. So, that is what happens. So, a typical example if I give, if you take the age of a particular class, let us say class 6 or 6 standard. Okay, if you take the random samples from 6 standard, or if you go and take the age value of a competitive exam, and there is a coaching center over there, and you are trying to take that age value, you will see a lot of deviation. Okay. Whereas here 6 standard, if you just take those age, probably it will be almost similar. Okay. So, that is what happens. You can have similar mean value reported, but you can have a large deviation. So, basically that characterizes the randomness of the associated process. So, that is why just mean will not characterize anything. You have to go to this variance, which says something about it, but variance also will not be enough. you will see that it is all those higher moments that has to be characterized. Then only a complete random process can be, or complete variability of that random variable you will be able to characterize it. Okay. And the best thing to characterize a random variable is this one. This provides all the information, because once you know the distribution, see it is all these average things, standard deviation, those came first before even understanding this means PDF or PMF, associated PMF. People started seeing, okay, if something is random, can we just measure some or guess something about that random variability. So, they started with mean initially, then they could see that, okay, if there is wider variability and smaller variability, still the mean is same. So, they went to the second order statistics, or that variance or standard deviation will define them. Okay. So, then they could see, okay, there is some more things that we can extract, but they could see that you go to the next higher order, probably something else will be happening. So, every higher order is required, but finally people could understand that it is just that PDF or PMF which characterizes everything, because once you know this, you can actually generate all the moments. So, if somehow you can get the PDF, you have everything. Okay. So, all the statistics related to it is already in your grip. So, that is why PDF is probably, and that is the relationship between PDF and all those moments, right. But anyway, so what we were discussing, that if I have a PDF, I can go to the first order or second order and all those things. So, this was my definition of variance. Let us see how it is related to those first and second order moment. So, if I just expand this, I can write, this is just the average value. So, this can be x square minus 2 x into x bar plus x bar square. Remember here, x bar is already the mean value, that is not a random variable. So, taking bar of that will return you the same value, right, because it is the same, every time it will be same thing. So, whether you take average or any other thing, you will be getting the same value out. So, now this averaging, suppose it has an associated PDF, it is just an integration, right. So, integration with addition and subtraction, that will be distributed. So, I can write this as well as x square bar minus 2, this 2 is a constant, x bar is a constant. So, that will come out from the integration, and it will be just integration of x into pxx. So, that should be another x bar plus this is constant. So, it must be x bar square, right. So, finally, what do I get? Minus this is 2 x bar square plus x bar square. So, this is nothing but x square bar minus x bar square. So, once you have evaluated your mean, and then through this process you have evaluated your second moment. So, just the difference of these two are your variance. Okay. So, calculation of variance, which was a measurable quantity people used to do, they used to always take every value from mean, how far it deviates, take the square of that, add all of them for all samples, divided by sample number. This thing can easily be now calculated if you know the probability of them. Okay. So, that was our target, that we wanted to, all these measurable parameter that people used to do, how do we correlate that with our this moment definition, right. So, we could achieve that. So, this we can write as x square pxx dx integration minus infinity plus infinity minus x pxx dx integration minus a whole square of that. So, that is all. Immediately we get our variance, and standard deviation is nothing but the square root of that variance, because just you do not want to cancel them out, you have squared it, and then you have taken the average of square. But if I want to see the actual deviation, so I need to again do a square root of that. So, that square root of variance is just the standard deviation, that is by definition. Okay. So, that is characterized by sigma, often that is square root of variance or square root of x square bar minus x bar whole square, right. So, this is how you get this sigma. This was the sigma which we were characterizing for Gaussian. So, you remember there were two parameters for Gaussian distribution. One was that mean, which is x bar. So, that m was actually x bar, and you can verify that. Take that Gaussian distribution, you plug in x into pxx, integrate it, you will be always getting this m back, where Gaussian was defined by that x minus m whole square divided by 2 sigma square, and again do that variance calculation, you will get back this sigma. Okay. So, this is what happens. In the next class, what we will do, so far we have defined all these things. In the next class, what we will try to do is, we will try to see some more relationship between these two particular part, that variance, mean, how they are related for a particular random experiment, when they are independent, they are not independent, how do means mean already we have seen, whether they are independent, non-independent, it is always addition of mean, but for standard deviation what happens, or variance what happens, can they be evaluated separately. So, that is something we will try to characterize, and then we will probably go into slowly towards a new definition which is called the correlation. Okay. So, that is something we will try to do. Thank you.